I guess I would be very happy to take this opportunity to introduce you a little bit about the research that we do in our lab. We have been trying pretty hard to we've been trying pretty hard to develop a new energy and environmental science and technology in our lab, and the approach that we take is to use molecular electrocatalysis. So a little bit about the background. We know that we currently face energy and environmental problems. Right? For example, the concentration of carbon dioxide in the atmosphere is increasing very quickly, and so there are a lot of issues related to it, the change of temperature and also the climate. Right? Then the carbon dioxide goes into the ocean, and that will lower the pH to make it acidic, and this is really dangerous for some life like the coral reef. They're basically just dying. Besides carbon dioxide and the carbon cycle, right, we also have some issue with the nitrogen cycle. For example, if the overuse of fertilizer has caused a lot of excess nitrate in the water, and then that can lead to problems like eutrophication, and that will basically take the oxygen out, and it's very dangerous, and it can damage a lot of life in the water. Right? Then, beside carbon dioxide and the nitrate issues, the industry is also producing a lot of volatile organic compounds, and these things, they go into air, they go into water, and it will cause a lot of problems to human health. Right? So a lot of these problems are somewhat caused by human beings using of chemistry. Right? So we are thinking that maybe chemistry should also be the cure in this case. So in our lab, we have been looking at some chemical reactions that might help in this regard. Right? So some of these reactions that you are seeing here, right? The first one is conversion of carbon dioxide to liquid fuels, right? And as you can immediately see that this will create a way of producing carbon neutral fuels. Right? And then the second one is a co-reaction of carbon dioxide and nitrate into organonitrogen compounds. Right? And then the idea is to take waste gas and waste water as reactants, and to produce some type of chemical compounds that are useful in medicine and then agriculture. The third one is interconversion between sulfur and lithium sulfide, and this reaction can be used to power batteries, and the so-called lithium sulfur batteries that can provide several times more energy, and can also be several times cheaper compared to the current lithium-ion battery technology. The last one is basically treatment of chlorinated hydrocarbons, chlorinated organic compounds in water, and that is to, of course, to do water purification, right? And what we want to do is we want to use electricity or solar energy to drive these reactions, right? And obviously, it has its advantages and also has some kind of issues to solve. And the advantage with using electricity to drive these reactions is now the power can be from renewable energy, right, like solar power. And the reactions will take place under very mild conditions, 1 atm room temperature in aqueous media, right? And also there's no need for additional chemicals to go into it, right? But there are issues with it, because these reactions, when you want them to happen electrochemically, right, they might not be that easy to happen, right? Even though that thermodynamics says these reactions should happen, but in reality, some of these reactions have never been reported, or some of these reactions are very hard to proceed, right? So what we need to do is we need to develop a good catalysis for these reactions to happen. Right? So that's what we have been doing in our lab. And the major material that we use, interestingly, to characterize all these reactions that I just talked about is this one, right? And in this you see a molecular structure. So that is a molecule called a cobalt-tyrosine, and we put this molecule onto the surface of a material that is called carbon nanotubes. Right? And the idea is to disperse these molecules on the surface of a carbon nanotube, and in this way we create a catalyst. And this catalyst, we call it a heterogeneous molecular catalyst. And the idea is when you have the molecules on the carbon nanotube support, this catalyst becomes heterogeneous, so that it can have the advantages of a heterogeneous catalyst. It can provide a high reaction rate, good stability, and it will be easy to separate. Right? Then this catalyst has this molecule as its active site, so it is molecular in nature, so it can enable mechanism-based optimization. So that's the advantage of this material. Right? Then I will just briefly talk about the reaction that we have developed with this catalyst. Right? So the first area is we basically take this catalyst to do electrochemical carbon dioxide conversion reaction. And with this catalyst, we're able to convert the carbon dioxide. So here basically you see a picture of a reaction cell that we use in our lab. And this catalyst is able to convert the carbon dioxide first to carbon monoxide and then to methanol. Right? And then these two reactions, they happen all on the same catalyst, so we call this domino catalysis. And then the final product is methanol, which is a widely used liquid fuel and also a chemical. And this catalyst is basically, I guess, still the only molecular catalyst that is able to do this reaction, to take it from CO2 to methanol electrochemically. And the first step from carbon dioxide to carbon monoxide has a pretty good Faradic efficiency of 90%. Then the second step from carbon monoxide to methanol is only 40% or so. So the second step, the reduction of carbon monoxide, is more difficult. Right? Then our mechanistic analysis has shown that it is the issue of the carbon monoxide. So the absorption of carbon monoxide on the catalyst site is quite difficult, right? And it goes on. It is also very easy for it to further also leave the catalytic site. So the reduction of the carbon monoxide is a difficult step. And based on the mechanistic understanding, what we can do is we can increase the local pressure of carbon monoxide and try to create an environment that can concentrate the carbon dioxide onto the catalyst surface. So with the reaction taking place at a high pressure, like 10 atm, we are able to push the conversion of the Faradic efficiency of carbon dioxide reduction to methanol to 85%. Right? And this has basically removed one of the roadblocks for commercializing this reaction. So at this moment, one of my students started a company trying to commercialize this technology, right, for methanol production. Then in the second area, it's still related to carbon dioxide to methanol conversion, but we do not just want to use electricity. We want to directly use solar energy to trigger this reaction. So now what we need to do is we still use this catalyst, but we have to put the catalyst onto a semiconductor. And in this case, the semiconductor can take in sunlight and generate electrons and use the electrons to directly carry out the reaction. Right? So in this case, we put the catalyst and we do some chemistry, right, to put it onto the surface of a silicon. And in this case, the silicon is a semiconductor. It will take in light, it will generate electrons, and to do the reaction. So this enables direct solar fuel production. And we have assembled this electrode, and this electrode works pretty well in this kind of reactor tested in our lab. It is able to convert the carbon dioxide to methanol with about 400 millivolt of photovoltaic generated by silicon. The selectivity is 8% and a reasonable current density, right? I mean, this is essentially the first molecular catalyst-based electrode photoelectrode that is able to convert the carbon dioxide to methanol, but the performance can still be improved, right? So what we did later was to pattern the surface of the silicon to create these kind of micro pillar structures that will be able to load more catalyst to optimize light absorption, and a layer and a structure that is able to trap the carbon monoxide intermediate that is more difficult to reduce. And with this, we're able to further improve the performance selectivity to roughly 20%, right? And then the current is to 16 milliampere per square centimeter. So we're advancing this performance for direct solar fuel production. So that's area 2, right? And then in area 3, we are trying to do gas and water treatment all at the same time. So this is still the catalyst, right? You know that it can catalyze carbon dioxide to methanol, right? the right cycle, right? And then that step goes through formaldehyde as the intermediate. Then the same catalyst is also able to treat nitrate, and it is able to electrochemically reduce nitrates to ammonia. That is the left cycle. And one of the intermediates here is hydroxylamine. And once you do these two reactions at the same time inside the same reactor, the formaldehyde and the hydroxylamine, they are going to couple with each other and to form a carbon-nitrogen bond. And then this thing can be further reduced, and eventually we get it to the product of methylamine. And then this is an organo-nitrogen compound that is often very useful precursor in pharmaceutical synthesis and also production of agricultural chemicals. Right? So this is actually a new reaction, right? Because no one has really seen this kind of reaction that is able to use the electricity to drive carbon dioxide and nitrate, right, to inorganic reactants, all the way and directly to form an organic product that is methylamine, right? So this is actually a new reaction that is discovered in our lab. And with this, now we are able to kind of like treat carbon dioxide and nitrate all together. And we further developed this reaction, right? So we advanced it based on the understanding of this catalytic mechanism. So we're able to switch the catalyst out for a different one, which is copper metal. Then we are able to make not just methylamine, but now ethylamine. And then we also use other organic amines in the place of this hydroxylamine to couple with the formaldehyde intermediate. And in this way, now we can do methylation of amine compounds. And the methylation is done from electrochemical CO2 reduction. So in other words, now we are using carbon dioxide as a C1 building block, right, to do methylation of these organic compounds. And the energy is, of course, from electricity, and it is renewable. Right? And this reaction happens in aqueous medium. So this area 3, right? And then in area 4, this is related to the interconversion between sulfur and lithium sulfide. And the idea is this kind of interconversion, as I said, right, it is lithium sulfur batteries. So lithium sulfur batteries are quite promising because they can provide several times more energy compared to the current lithium-ion battery. But there are some challenges with it. One of these is that you have to run the battery with just a very tiny amount of electrolyte so that you can get a high energy density. But when the electrolyte amount is very low, you see that the reaction becomes very difficult, and there is a kinetic barrier associated with that. Right? And we found that that kinetic barrier is related to the reduction of dissolved lithium-2-sulfur-4 to lithium-2-sulfur-2 and the lithium sulfide solid products. Right, so after identifying these potential limiting step, we're able to apply our catalyst and then to reduce the kinetic barrier. And then that can make the battery to operate under these more application relevant conditions. Right? So that is just one step, towards the practical development of this future battery technology. Right? And then we move on to the last area, I believe, right, which is related to more water treatment, right? So this is one of the examples that we deal with in our lab. It is dichloroethane, right? So this is a very commonly used chemical, and it gets into the water bodies, but it takes very long for it to naturally decompose or to be treated by methods like a degradation. Right? And this chemical is very harmful to organs and then also neural systems, all these kind of things. So it's quite a toxic molecule. Right? So we would like to develop a reaction that are able to take care of it. Right? So in our lab, we of course use electricity to drive the reactions, and it is still the catalyst that I just talked about. And in this particular reaction, we are able to basically take the chlorine atoms off this molecule and to produce it as a chloride, which is not toxic, and then it will form ethylene as a product. And ethylene is also not toxic, and it will come off the water as a gas. And if you capture the gas, ethylene can also be a useful chemical. Right? So this is the way, the reaction we use to treat this. chemical. Right? And then the idea is to use electricity to drive the reaction, right? So that we can have faster decomposition, it will be powered by renewable energy, and there's no need for additional chemicals. Right? And simultaneously, we can produce ethylene as a valuable product. And our catalyst is very good because compared to the one that people have tried before, we have the best Freilich efficiency and the lowest overpotential, meaning that the reaction is very efficient. So a little bit of idea how we actually do this water treatment, right? So we have this catalyst, right? If you still remember, molecules are supported on carbon nanotubes, right? Then we put the carbon nanotubes onto basically a filtration paper, right? And then we create a membrane. And this type of membrane, right, it is not just a membrane that can be used for water filtration. It can also be applied, an electrical potential can also be applied to the membrane to do electrochemical degradation of the pollutants in water. Right? So with this, we can do a water filtration, but not the regular water filtration, but a electrified water filtration. The water is being filtered through the membrane. At the same time, electrochemical reaction is happening to decompose the chlorinated organic compounds. So with that, we can actually get to quite a high yield of the pollutant removal, and the decomposition rate of dichloroethylene. Dichloroethylene is about 98%. 98%. Right? So this is related to, I guess, volatile organic compound in water and how to treat them. So I guess with that, I'm ready to conclude my talk. Right? So hopefully I have shown you what we are trying to do. Right? We try to use new materials, new catalysis, and to develop new reactions and create new opportunities to tackle energy and environmental challenges that we are facing. Right? And of course, as I said a few minutes, I guess earlier, all these experiments were done in my lab by my students and postdocs, right? So they should really take the credit. And I should also thank my collaborators, Professor Liang at STAC, and who provided us with the catalyst material initially, and then my colleague, Professor Ilan Malic at Yale University, who really helped us with the water filtration project. And the projects were funded by the National Science Foundation and the Department of Energy from the United States. And I, of course, thank you for this opportunity to share my science. And I guess I do have a final slide, right? So I hope it's moving. Yeah, so many thanks goes to USERN and also the local host, Russian Armenian University. Thank you so much.